Hey class, welcome back to our lesson on three-dimensional figures and cross-sections. In the previous lesson we talked about vertices, faces, and edges, and what we're going to talk about in this particular video is Euler's formula. His name is pronounced Euler. He's a mathematician, and he was noticing some stuff about three-dimensional figures and a relationship between vertices, faces, and edges. So let's go ahead and talk about his relationship that he found. So remember in the previous lesson, in the previous video, we were naming vertices and edges and faces, right? And so we actually talked about these two diagrams here, but just in general, the face, the face here, the edge where two faces meet, and the vertex where there's a sharp pointy point. Now, mathematician Euler he discovered a neat relationship with polyhedrons and the number of faces, vertices, and edges. And this is what he had discovered, that the number of faces and the number of vertices is going to always be equal to the number of edges plus 2. That's Euler's formula. The number of faces plus the number of vertices is going to be equal to the number of edges plus 2. So that's Euler's formula. And if you don't believe me, remember the last video we just worked on. So we had our diagrams, and remember what Euler is saying. The number of faces and the number of vertices, in this case 5 and 5, is equal to the number of edges plus 2, is 8 plus 2. True. 10 is 8 plus 2. The number of faces and the number of vertices, 6 and 5 is 11, is equal to the number of edges plus 2, 9 plus 2, 11 and 11. Isn't that neat? So Euler he discovered that, and now he has a formula named after him. So if you want a formula named after you, discover something cool. Now the key to this lesson, of course, as the last one, is visualization. So let's keep that in mind. Remember, it's the number of faces and the number of vertices is equal to the number of edges plus 2. It might look like the word 5. It might look like whatever it is that you need. So whatever you can do to memorize that. So let's see this in play. Now we're going to make this crazy looking polyhedron, and we're going to see if Euler's formula pans out. Okay, so the question here is, how many vertices, edges, and faces does this polyhedron have? And then we're going to verify Euler's formula. So just like we did in the previous lesson, we're going to count the number of vertices first. Okay, so we have 1, 2, 3, 4, 5, 6 pointies there. 1 in the back, 2, 3, 4, 5, 6 pointies there. So that's 12 vertices. So we have 12 vertices. And now we're going to look for the number of edges we looked for. And the edges are the corners where two faces meet. So here's an edge, 1, 2, 3, 4, 5, 6 edges. I went around the side first, right? You got to visualize. I went around the side first. So 6 edges there. Now I'm going to go around the top. 7, 8, 9, 10, 11, 12. And then around the bottom. 13, 14, 15, 16, 17, 18 edges there. Okay, so we have 18 edges. And then lastly, the number of faces. So we're going to look for the number of faces now. So we have the front here, right? So we have 3 in the front, right? 1, 2, 3. 3 in the back, 4, 5, 6. 1 at the top, 7. And 1 at the bottom, 8. Okay, so we have 8 faces. And now, can we confirm that with Euler's formula? So you remember Euler's formula. Remember like the word 5. So Euler's formula says the number of faces plus the number of vertices is equal to the number of edges plus 2. So it's like the word 5. So faces and vertices is 20. Edges plus 2. 18 plus 2, 20, 20. Win. Okay, win. So we're all set there. Now what we can do is apply that formula for some algebraic concepts as well. So now we can do algebra. Take a look at this particular example. Here we have a polyhedron, like this crazy looking soccer ball-y kind of thing. And we're going to use Euler's formula to find the missing number. So what's missing? The number of faces. We have the number of edges and the number of vertices. We can find the number of faces. So how do we do that? Well, what is Euler's formula? Again, that word 5, F-I-V-E, kind of like that, but 5 plus 2. So we plug in what we know. We don't know the number of faces, that we don't know, but we do know the number of vertices is 20, And we do know the number of edges is 30, and we know that the formula has a plus 2. So the rest is algebra, right? Good old algebra. Well, f plus 20 is f plus 20. 30 plus 2 is 32. All we have to do now is subtract 20 from both sides. So we subtract 20, and then we have good old, the number of faces is equal to 12. So this is a 12-faced polyhedron. Okay, so the number of faces is actually 12. And that's Euler's formula at work. Now what we're going to do is take a little bit of a brain stretch. We're going to visualize our three-dimensional shapes, and we're going to make something called nets. Now you may wonder, what is a net? A net is what happens if you unwrap a three-dimensional shape. So in this particular example, I'm going to take this three-dimensional shape we've used, and hopefully it won't be too challenging. Clearly I'm having a little bit of trouble to unwrap this shape. So I'm going to unwrap this shape, and the net is the resulting figure, basically the resulting diagram. And so when I unwrap this shape, I end up with a net. So remember, that was like a rectangular prism. This is the net. Okay, so notice I had my faces and the top and the bottom, right? So the right face, the front face, the bottom face, and all that, and then I had the top and the bottom. And so that's what making a net is. We have to be able to visualize that for each of these diagrams. And so we will do just that. So take the pyramid. Okay, so we're going to make a net of the pyramid. And the way I make a net is I begin with the base. Okay, so if we are looking down at this pyramid, look down. If we're looking down at the pyramid, the base would be in the shape of a quadrilateral, possibly a square. We don't know, but we can make it look like that, and then we can work with it. So that would be the bottom. Okay, and then what would happen? All of the sides unfold. The front side unfolds. The right side unfolds, the back side unfolds, the left side unfolds. And what would happen in this particular example, our pyramid would unfold. And it would look just like this. And so we make our net this way. Okay, so we had our bottom, and then the sides unfolded. And I'll do the same thing with the wedge of cheese. Okay, so with the wedge of cheese, I'm going to look down, and I'm going to start, personally, I'm going to begin with the bottom. Okay, so this would be the bottom of my wedge of cheese. And if I picture my bottom of the wedge of cheese, I'm just going to unfold it this way. The next face, next to the bottom, is actually the left face. So I'm going to make the net of that left face. And it's a skinnier rectangle, right? It's that skinnier rectangle. And then would be the top face, unfolded after that. So as I visualize the top face unfolding, it would be another longer rectangle, similar to the bottom. But what about the front face and the back face? They're triangles, right? So I can make a triangle for the front and a triangle for the back. Remember, the key to this is visualization. So we have to visualize what's occurring, and we have basically unwrapped it. That is a net. We're making a net. So what about this hexagonal polyhedron? It's the same thing that we did with with our original rectangle, original rectangular prism when we unrolled it. So instead of working from the bottom from this, I'm going to visualize unwrapping the sides. Now we know that there are 6 sides to here, 6 faces around the side, the front 3 and the back 3. So there are 6 around the side, the front 3 and the back 3. And so I'm just going to draw those out. So there's 4, 5, and 6. Okay, so we had our 6 sides unwrapped, and then we had our top that's a hexagon, and the bottom that's a hexagon. And we can put them anywhere. It won't really matter. So that would be the top and the bottom. And again, it won't matter where you put them, but that would be the net. And the whole thing is about visualizing and unwrapping. Now, why do we do this? Because we're going to see Euler's formula in action on 2 dimensions, and it's going to be kind of interesting. Okay, so we're gonna check out Euler's formula in 2 dimensions. And so I have a couple of examples here. We're going to use nets to verify Euler's formula. So the first thing we do is with this hexagonal polyhedron, we're going to verify Euler's formula for the net of the solid at the right. Now, it's the same thing we just unwrapped here, right? It's our hexagonal polyhedron, so we know how to do it. There are 6 sides, right? So we make our 6 lateral faces, as we'll learn in a little bit. So there's 3, and 4, and 5, and 6. And then our 2 hexagonal top and bottom. So a hexagon for the top and a hexagon for the bottom. And what we're going to do is confirm Euler's formula. So how does that work? We need to count the number of vertices. Now remember what the vertex is. It's the pointy parts. In this particular net, we can look at the net and identify where the vertices will be. So how are we going to do that? Here would be a vertex, and here would be a vertex. So that's 2. Now this is a fold, isn't it? So 3, 4, and another fold. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 vertices. But that's not it, because we had other vertices as well. 15, 16, 17, 18, 19, 20, 21, 22 vertices. So when we're looking here, we have 22 vertices for this particular figure. And so that's our number of vertices. Now what about the number of edges according to this particular diagram? Remember what the edges are. The edges are the folds where they folded, so we can count those up. And here's how I'm going to count them, right? So we have an edge here, that's a fold, and 2, and 3, and 4, and 5, and 6, and 7. Okay, then 8, and 9, 10, and 11, 12, and 13, 14, 15, 16, 17, 18, 19. And what about these? 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Isn't that an interesting number? So 29 edges, and that's an interesting number, and so we're going to put a little star there. That's an interesting number. And then lastly, the number of faces. The number of faces should be easy to count. Okay, so the number of faces should be a little bit easier to count. They're just the flat surfaces, right? So let's count them up. We have 1, 2, 3, 4, 5, 6, 7, 8 faces. Perfect, perfect. Now, should Euler's formula work here, right? It absolutely should, because it works. We've proven it before. We've seen it in action. We know it's a solid formula. So will it work here? Okay, will it work here? Well, let's take a look. If Euler's formula is that, you remember the number 5 plus 2. Faces and vertices is equal to edges plus 2, right? So we look at this and we're thinking, it's not working. It's not working because 22 and 8 is 30, and 29 and 2 is not 30, it's 31. So what's the deal here? There's a couple of deals here. There are things that we may have already counted, and that will make an impact. So take, for example, the vertices. We may have already counted some vertices, like these vertices down here, right? These 4, and then these 4 up top. That's 8 vertices we may have already counted. But more importantly, what about these 2? Remember, this is a net. This is totally unfolding, right? It's unfolding. So we may have double counted these vertices. That's 10 vertices we may have overcounted. And what about the edges, right? So what about the edges? Remember, we unfolded this. And so we have an edge here and an edge here where they met. That's the same edge, right? And then what about the edges of the top and the bottom? Those are the same edges. So did we overcount? Maybe. But Euler's formula would still work because even if we just consider the edges, right? Let's ignore the fact that we had overlapping vertices. What if we double count that one edge? We're actually at 28 edges, right? Now Euler's formula works. 22 and 8, 28 and 2. It's the same number. It's going to be 30 no matter what. So what happens is with a net in a 2D diagram, right? So this is Euler's formula in 3 dimensions. Euler's formula in 2 dimensions is actually a little bit different. It's f, the number of faces plus the number of vertices plus the number of edges plus 1. That's Euler's formula in 2 dimensions because of the fact we have overcounted. Now, how do we know this is true? Because of the previous activity, right? That one question we had, it was the same shape. It's still a hexagonal polyhedron. This is no doubt the case in the number of vertices and edges and faces, and no doubt Euler's formula works. But when we use a net, look at how these numbers change, right? So there's some interesting stuff that goes on, but we have to use visualization in order to see it in play. So Euler's formula in 2 dimensions, we have to account for overlap someplace, and we'll always have like a value of 1 as the overlap in 2 dimensions. How's that true? Well, let's do the same thing for the next example. And this will be it for the video. So here's another polyhedron, 3 dimensions. Let's make a net. Okay, so we know it's got a trapezoid for a front and a trapezoid for the back, but let's unfold it. Okay, so we have 1, 2, 3, 4 rectangular faces. So we can make 1, 2, 3, 4 rectangular faces. And we have a trapezoid front, so we can make a trapezoid front and a trapezoid back. A trapezoid back. So this is the net, right? So what do? We count the number of vertices first. And vertices are the corners, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 vertices. Let's not worry about the overlap for right now. We have the number of edges. Remember, this is going to be the interesting part because the last 2 sides were together. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 with a question mark or a star. And finally, the number of faces, which is pretty easy to count. So 1, 2, 3, 4, 5, 6. So is this Euler's formula at work? Absolutely. 14 and 6 is 20. 19 plus 1, right, is 20 as well, because we're working in 2 figures. Or if we take into account the overlap, right, everything completely works out. So this completely checks. We just have to remember about the overlap. So that is it for this video. We'll come back for a 3rd one where we start talking about cross sections, and that could be a whole lot of fun. So hope you enjoyed it. We'll come back later.